We have seen two methods for incompressible flows, the artificial compressibility method and the stream function vorticity method. Both of these have their own specific limitations. The artificial compressibility method can be used for 3D but not for time dependent flows. The stream function method can be used for time dependent flows but not for 3D. We will look at a pressure equation method which can be used for both 3D and time dependent flows, and but we will explain this method in a specific way, and the idea again is to follow the method and work out the details at a later stage. So, the idea of the pressure equation method is already the germination is there in the stream function vorticity method, where we derived an equation for pressure. So, we look at a method which is applicable both for time dependent flows and 3-dimensional flows at the same time. It is not either for this or for that. This is based on the idea of solving an equation for pressure together with the momentum equations, and how this equation for pressure is constructed we have already seen when we discussed the stream function vorticity method, in which we said that it is possible to manipulate by taking the divergence of the momentum equation. We can derive an equation for pressure, and that we showed how to do for a 2D flow. For 3-dimensional unsteady incompressible flow with constant properties, the same Poisson equation for pressure can be written in this compact way using the index notation format, that is dou by dou xi of dou p by dou xi. In this term the index I is repeating, and therefore this implies sum over the 3 values of I that it can take. So, that makes it dou by dou x of dou p by dou x plus dou by dou y of dou p by dou y plus dou by dou z of dou p by dou z. So, that is the Laplacian of p here, and on the right hand side we have minus rho dou by dou xi of dou by dou xj of ui uj. Okay. So, what do we have on the right hand side? Density is known property and the velocity field. So, this equation here, pressure equation, implies, as we have seen earlier, that if the velocity field is known, then pressure can be evaluated. Okay. So, and we also know that for UVWP to be a true solution of fluid flow, then the velocity field, that is UVW, which are functions of x, y, z, t, used to evaluate the pressure field, should satisfy the continuity equation, while the pressure field so derived when substituted back into the momentum equation should produce a velocity field that satisfies the continuity equation. So, we need to solve both the continuity equation and the momentum equation. So, if we are evaluating pressure from a velocity field, this pressure when substituted into the momentum equations to get a velocity field, that velocity field should also satisfy the continuity equation. So, that kind of necessary condition is there for a UVWP field to be considered as a true solution of the Navier-Stokes equations. So, using this idea, it is possible to construct a sequential time marching method. We will see we will start with an explicit method of successive evaluations of pressure and velocity, which is as follows. So, you consider the discretized form of the momentum equation. Okay. So, we have dou u by dou t plus dou by dou xj of ui uj equal to nu times dou square u by dou x dou xj minus 1 by rho dou p by dou xi. So, that is the momentum equation. We are writing this as a discretized form, so as to distinguish it from the continuous form. We are using this delta here, and we have taken this term onto the right hand side. So, that we have dou ui by dou t equal to del ui by del t equal to del by del xj of ui uj plus nu the kinematic viscosity times del by del xj of del ui by del xj minus 1 by rho del p by del xi. These dels here are difference operators. Okay, you could be using upwind scheme here, you could be using the central scheme for this, you could be using a central scheme or whatever other scheme that you want to put here. Okay, so it does not matter what it is. Okay, you choose the appropriate ones for the discretization operators for each of these. Even here you can use forward first order, second order, central, all those kind of things can be used here. But this is the discretized form of continuity equation. Now we can write this simply as a forward differencing and write this as uin plus 1 minus uin by delta t. If we do that, then we get an explicit solution, scheme of solution can be written as uin plus 1 minus ui divided by delta t, we take the delta t to this side, delta t times all the right hand side terms which are evaluated at nth time step. Okay, so this is the uiuj term del by del xj of uiuj with a minus sign because it is taken to the right hand side, and the diffusion term here. So this is evaluated as at nth time step, and even the pressure gradient is evaluated at the nth time step. Okay. So here we are not doing any cheating, we are just writing it like this. Okay, we are putting down a scheme of solution. Okay, so that scheme of solution is saying that forward difference for the time derivative and explicit differentiation. As of now we are not specifying what these difference operators should be. We can use, for example, the upwind differencing and central differencing, and this we will see. Okay, so now we take divergence of this equation. So that is dou by dou xi, because I is the index here. So when we take the divergence, we get dou by dou xi of uin plus 1 minus dou by dou xi of uin. So every term is put as dou by dou xi operator is put here, and delta t is a constant, dou by dou xi of this whole thing minus delta t divided by rho times dou by dou xi of this particular term here. Okay. And in this particular, this is the modified momentum equation, and here we want to impose the idea that if we get the from the computed uin n, that is at the previous time step values, we want to evaluate p such that if this p is substituted into the momentum equation, which then we get uin plus 1, this uin plus 1 should satisfy the continuity equation. And what is the continuity equation? Dou by dou xi of uin plus 1. So we want a velocity field such that it satisfies the continuity equation. So this term is 0, and we are starting, we already have the previous time step value. The previous time step value must also satisfy the continuity equation. So dou by dou xi of uin must also be equal to 0. So when you look at this equation here, if you impose the condition that uin plus 1 must satisfy the bound the continuity equation, then this is 0. Since uin satisfies the continuity equation, because you are now moving on to uin plus 1, and by then you have already got uin, and for uin to be a correct solution, it must satisfy the continuity equation. So dou by dou xi of uin is also equal to 0. Okay. So if we set these things to 0 here, 0 this, because this would have satisfied the continuity equation, and this to 0 because we want it to satisfy the continuity equation. Okay. And so that gives us a condition for pressure. So these two are 0, and we can now cancel out delta t here, and we will get an equation for pressure at nth time step like this. So this equation contains on the right hand side velocity at the nth time step, and these are also velocities at nth time steps. So these are all explicit terms, and since we have already got uin and we are moving on to uin plus 1, we use this one to evaluate pressure, okay, and this pressure is at Pin. So that means that Pijkn. So we put that into this equation here, and if you put that P here, and then all this right hand side is known and this is known. So from this we can get Uin plus 1. So we start with Uin and then we get Pin and we substitute in this and then we get Uin plus 1. Okay. So that is what is shown here. So these equations permit evaluation of this equation here, permit evaluation of Pin from continuity satisfying Uin. So this pressure field can be used to evaluate continuity satisfying Uin n plus 1 here. So this can then be used to obtain Pin plus 1. So once you put once you get Uin plus 1, you can put this on to n plus 1 here and then get Pin plus 1. Once you get Pin plus 1, you can put this on to this, you can get Uin plus 2, and then you come here to get Pin plus 2. So in that way you can use these two equations alternately to get Uin plus 1 here. From Uin you first solve this to get Pin, and then you put that Pin here to get Uin plus 1, and you put this here back to get Pin plus 1, and then you move on like this. So you are satisfying the momentum equation and pressure equation, which is obtained by imposing the condition that the velocity field that we are getting here satisfies this, and each of these is explicit method. So we start with the continuity satisfying Ui0, get Pi0 from this, and then put this Pi0 here and all the Ui0s here and get Ui1, and then you put Ui1 here and then we get Pi1 and then move on like this. So this method is applicable for 3-dimensional flows and also time accurate flows, and it is explicit. Okay. So in this way this method is differentiated from the two previous methods by the fact that we are solving an explicit equation for pressure along with the velocity, along with the momentum equations. In the stream function vorticity method, we completely eliminated pressure, and it is not necessary for us to evaluate pressure in order to get U and V. In fact, we need not evaluate. If you are not interested in P, then you need not evaluate U, and you need not evaluate P. You can get Ui and Vin plus 1 without having to compute pressure. But here we have to compute pressure, and we are doing it in a hopscotch manner. First you get this, and then you get this from initial condition. Okay, initial condition, which is in which the initial condition is such that the velocity field satisfies the continuity equation, so that this is 0 here. If it does not become 0, then the initial condition does not satisfy the continuity equation. It is not a true velocity boundary condition. Okay, it is not a true initial solution. So we need to adjust that here. So we can construct this. We can also construct an implicit pressure equation by in a very similar concept. We got this equation here for the equation for pressure by writing this in as explicit form here. But if you make this implicit, if you make the velocity field implicit here, so then this is the equation, and we started by putting this to be equal to, we made an explicit scheme like this. If you make it implicit, then this becomes n plus 1 and this becomes n plus 1. So that is what we have here, and we take divergence of that, and we have this as n plus 1, this will still be there, and this whole thing is such that we put n plus 1 here and n plus 1 here. We use the same argument that the new velocity field Uin plus 1 must satisfy the continuity equation. So this equal to 0. The old velocity field anyway satisfies the continuity equation, so this anyway equal to 0, and then you have an implicit equation for pressure which is given by this thing here. So, now if you want to evaluate pressure at n plus 1, you need to know the velocity at n plus 1, but you do not know the velocity at n plus 1, you can evaluate it only if pressure is known. So, you have an implicit evaluation of velocity here which requires p at n plus 1 and all the values u at n plus 1. So, what we do is that we start with some guess velocity field, okay, and then we can use this to get pressure field at n plus 1, and then we put this pressure field here, then we get new velocity field, we put this back into this and then we get p n plus 1, we put this back here and then we get u n plus 1. So, just to evaluate the velocity and pressure field at n plus 1, we have to solve this and then we have to solve this and then go back and solve this and update. We need to iteratively solve these things together to get u n plus 1 and p n plus 1 which satisfy the discretized momentum equation, the discretized implicit form of the momentum equation, and a discretized pressure equation subject to the condition, derived subject to the condition that the velocity field at n plus 1 satisfies the continuity equation. So, in this way we can solve implicitly for pressure. This implicit method is differentiated from the explicit method that we have here, in which from starting from ui 0 we put that here and get pi 0 and we evaluate all pi 0s at over all ijk's here, and then we immediately go on to this and solve this for all ui 1s uijk at first time step, and then we come back here and then solve in one go the pressure at all ijk's, and then we come back here. So, we are not solving repeatedly for ui n plus 1 and pi n plus 1 like that. You get this ui n plus 1, immediately go on to get pi n plus 1, and you are not coming back to ui n plus 1, you are going to ui n plus 2 in this case. Whereas, in the case of implicit pressure equation, you are solving this for you are solving this equation here for pressure at pi n plus 1 with an assumed velocity field at n plus 1, and once you get this pi n plus 1 we substitute here and then we solve this one to get ui n plus 1, and because now ui n plus 1 has changed, the velocity pressure field also gets changed. So, you put this back here and then you do this, you solve these iteratively together until convergence, and at that point you have pi n ijk n plus 1 and uijk n plus 1. So, having gotten a solution for these two equations simultaneously, then you go back and then solve for ui n plus 2 and pi n plus 2 again by solving these two iterations, these two equations iteratively. So, at each time step you are moving back and forth between this equation several times until you get a converged solution, and then only you move on to n plus 2. Whereas, in the explicit method you solve this once and then you come here and then you solve this and then you solve this and then you solve this. You are not coming back to both the equations in the same time step. You solve for one time step, you solve it once. Okay. So, what is the difference? This is an explicit solution, this is an implicit solution, and when you are looking at coupled equations and all that, implicit solution is better, it is more stable. So, in that sense you can have probably much larger delta t's that are possible with this than with this, and that is the advantage that we get. This method is also applicable for 3D time accurate flows just as this method is, whereas in the explicit method we are forced to choose very small delta t's so that we do not get into instability problems. In the case of implicit methods we can drive this to steady state and get a steady state solution, just as we are, if we are not interested in time accurate solution, we can take large time steps and then get to the steady state solution. So, that is one advantage of this. Okay. So, this pressure equation method is one which is applicable for 3D time accurate flows. In the next lecture, we will look at a pressure correction approach which is similar to this in some sense, but one particular form of the pressure equation method which is known as which is a semi-implicit method has proved to be very robust for a range of incompressible flows, both external flows and internal flows, and that is a method that we will look at in the next lecture for the solution of incompressible flows. So, that method is a semi-implicit method, whereas here we have seen an explicit method and an implicit method, in both of which we are using a pressure equation to be solved along with the momentum equation. In the pressure correction method that we are going to look at, we are going to use a semi-implicit method which is not fully implicit, not fully explicit. It is a semi-implicit method. Again we are solving some modified form of the pressure equation and momentum equations together, and that is a method that we will discuss in the next lecture.